Hi, I'm Jeff Green, and welcome to Crash Course Math. That's right, John. That's right, Hank. Crash Course. Because I had the idea first. I had the idea of this crazy desk filled up with all kinds of weird and awesome stuff before any of you did. I had the idea of rocking the awesome shades before any of you, and I most certainly had the idea of Crash Course before any of you. Because I'm Jeff Green with Crash Course, wait for it, Math. In Crash Course Math, the only crash course that you need, better than any of those other crash courses, we have swag, we have style, and we have class. That's right, check out my shades, Hank. And the one thing that you will see in Crash Course Math is that we will strive to bring the best education in math while making it the dopest education in math. That's right. And in Crash Course Math, we have awesome intros too. So in this episode of Crash Course Math, we have something special. That's right, John. That's right, Hank. I'm gonna one-up both of you. We don't have no mystery documents with electric shock pens that we all know, that's right, John, we all know are fake. The viewers are watching. The viewers know, John. Trust the viewers. We don't have any open letters where we swivel around our chairs, and we've got something better than those mystery documents and open letters. We've got the math problem of, wait for it, math. And in this math problem of math, what we are going to see is an amazing AP Calculus AB question, just to prepare all those calculus students out there for the AP test. The volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes. For 0 less than t less than 12, the graph of r is concave down. The table above gives selected values of the rate of change r prime t of the radius of the balloon over the time interval 0 is less than equal to t less than equal to 12. The radius of the balloon is 30 feet when t equals 5. Note, the volume of a sphere of radius r is given by volume is equal to 4 over 3 pi r cubed. A. Estimate the radius of the balloon when t equals 5.4. Using the tangent line approximation at t equals 5. Is your estimate greater than or less than the true value? Give a reason for your answer. B. Find the rate of change of the volume of the balloon with respect to time when t equals 5. Indicate units of measure. C. Use a right-Riemann sum with the 5 subintervals indicated by the data in the table to approximate integral from 0 to 12 r prime t dt. Using correct units, explain the meaning of integral 0 to 12 r prime t dt in terms of the radius of the balloon. D is your approximation in part C, greater than or less than integral 0 to 12 r prime t dt. Give a reason for your answer. That's right, this is a calculus problem. They've got crazy stuff in here. They've got DTs, that awful little thing that so many calculus students keep forgetting. Or at least some calculus students. I know a few for certain who... It's a very common problem in calculus students. I'm certain of that indeed. Regardless, they've got fancy DTs. They've got Riemann sums, And for our purposes, we've got to solve this math problem of math. Now, let's go to the think balloon. That's right, not the thought bubble, the think balloon, because we're thinking about balloons. And this one's got a lot of hot air. For part A of this problem, we intend to find the radius of the balloon when t equals 5.4 using the tangent line approximation at t equals 5. The radius of the balloon is expressed using the integral of r prime of t, or r of t. Since we already know that the radius of the balloon is 30 feet when t equals 5, we can identify that the radius at 5.4 is 30 feet plus the addition of radius over the interval from 5 to 5.4, which is evaluated as the change of time over the duration between 5 and 5.4, using the rate at 5. The rate at 5 is expressed by r prime of t, which is 2 feet per minute. Therefore, we can use 2 feet per minute times 0.4 seconds, the duration between 5 and 5.4, added to the initial radius 30 feet at 5 seconds, to identify an estimation using the tangent line approximation at t equals 5. This estimation we identify as 30.8 feet. Since the graph over this duration from 5 to 5.4 is changing at a decreasing rate, therefore concave down, the estimate is greater at 5.4 than. For part B of this problem, we must identify the rate of change of the volume, which we can identify using related rates. When we derivate the entire equation that we are given for volume, V equals 4/3 pi r cubed, we identify that the change in volume over change in time is equal to 4 pi r squared times the change in radius over change in time. Plugging in the points that we are already given at t equals 5, we can identify that the change in volume over change in time is equal to 7,200 pi feet cubed per minute. For part C of this problem, in order to identify the right Riemann sum to solve the integral from 0 to 12 of r prime t dt, or in other words, to solve for the change of the radius in feet from 0 minutes to 12 minutes, we must first look at the data points that we are given, and using all the right side data points being the data points when t equals 2, 5, 7, 11, and 12, we must identify a Riemann sum as provided here in order to solve for this quantity. For part D of this problem, we can use the fact that we identified in part A, that r of t is concave down, to identify that the entire function is changing at a decreasing rate. Therefore, we can identify that r prime is decreasing over 0 to 12. Knowing that r prime is decreasing, we know that our approximation in part C must be less than the actual value, because the actual value is estimated at a different point. So in today's math problem of math, we've seen a lot of crazy calculus stuff, like Riemann sums, dt, that awful little dt that's such a common problem among calculus students that I don't just keep talking about to make that one small percentage of calculus students feel better about consistently missing it on their FRQ, like despite all the crazy calculusness of this problem, here at Crash Course Math, the real crash course, we intend to prepare you for that AP exam, Advanced Placement IC. I don't always take AP tests, but when I do, I talk like that guy from that Dos Equis ad. So, this AP test, you will be ready for that crazy calculusness, because we here at Crash Course Math prepare you with crazy math problems of math. That's all for Crash Course Math today. Jeff Green out.